This conference will now be recorded.
Hello everyone, let's just wait for one more minute before we start today's presentation. So, good afternoon, or good morning, or good evening, everyone. This is the Water Talks, the second presentation of the Water Talks. Water Talks is an initiative from the Early Career Society of AquaWatch, and this is a way where we are trying to advance the diversity and equity in aquatic remote sensing by providing a stage for people from underrepresented countries to present in the GeoAquaWatch community. And today I have the great pleasure to introduce Daniela Rivera Ruiz, who is an environmental engineering, graduated from the University of Playa Ancha. She holds a master's degree in agricultural engineering with a specialization in water resource and is currently a doctoral candidate in water resource at the University of Concepción in Chile. Her doctoral thesis project is focused on developing methodologies to detect cyanobacteria blooms in Araucanian lakes using satellite imagery and machine learning techniques. Daniela has served as academic at the Faculty of Science, University of Bio, where she's instructed courses in hydrology and geographic information systems for satellite imagery to natural resources. I would also like to ask you to write questions in the chat. And if you want to have a certificate for attendance, just type your email in the chat and we will get to you. So, Daniela, the floor is yours.
Thank you so much for the kind presentation. I just wanted to start first expressing my gratitude to the AquaWatch community for providing us the opportunity to present our work through these water talks this year. So I personally feel very fortunate to be amongst researchers from whom I've learned so much from. So before I start this presentation, I will switch off my camera so to prevent any problems with the internet connection. So let's see. Okay, let's see. So this talk will cover two main topics. The first, I wanted to offer a brief overview of the current state in Chile. Can you hear me? Yes.
Yes, it's
Yeah,
working.
we can see your
Okay,
presentation.
something happened and I was not sure what, but okay. So I'll just continue. So like I said, I just wanted to tell you a little bit about how it is to study and work here in Chile. And I also wanted to give you a little bit of an overview of how the current state is in our country. This will cover the way research has been developing here, our limitations, and the gaps we're striving to fill, which I believe is a great opportunity to share with the community. Then I will transition to the core of this talk, which is centered on our ongoing study, which is the sensitivity of machine learning models to atmospheric correction methods over Lake Amatitlán. Here, we will explore the methods and the main findings of this research. After that, I will also share some future perspectives of what our research is going to look for in the next years, and also extend my acknowledgements to people that have supported this research. So, like Igor already said, I am an environmental engineer, environmental and civil engineer actually, that originally from Valparaíso, Chile, which is located in south central or central Chile. I'm currently working on a doctoral degree in water resources at the University of Concepción, which is located a little bit further down in Chile, in Chillán. And in April this year, I was fortunate enough to become a part of a research group at the Ibero-American Institute of Sustainable Development. This institute is within the Autonomous University of Chile in Temuco, so even further south. I'm moving further south every time. So at this institute, my computer is going black. I'm not sure if this is for the presentation, but okay. So at the Institute, I am a research assistant. I'm working within two groups, two projects funded by the National Agency of Research and Development that are led by Francisco Correa. The name of the projects are Climate Change and Multiple Local Stressors in Freshwater Ecosystems, and a model to monitor the integrity of freshwater ecosystems. Here we are really lucky because we are able to monitor environmental, biological, and water quality parameters at a basin scale level throughout different climatic gradients in our country. So we are actually covering most of the watersheds from the very north in the Loa River to the most austral areas in Chile. So in addition to these main projects that we're working on, we're also developing other projects within the institute, which is they are very supportive in supporting our ideas. And what we are doing here is specifically is monitoring the water quality parameters and macroinvertebrate diversity in watersheds that were severely affected by this year's wildfires, which were one of the biggest recorded in Chilean history. So I should mention that most of my colleagues are from a biology or natural resources background. And while we do have a forest engineer with extensive background in remote sensing, there is actually no one else that is focused on satellite remote sensing of inland waters, which is a reality that most research groups have actually, at least here in Chile. So this is actually where I will be mostly contributing in the near future. The idea is to integrate the study of lakes through satellite remote sensing, which is the topic and the methods that I'm using in my doctoral thesis project. So in the next slide, it will become quite clear why I actually also decided to move to Temuco, which is actually about an 11-hour drive from Valparaíso, my hometown. So Temuco, which is here, is the capital of the Araucanian region. Here we can find the starting point of the North Patagonian lakes from Lake Colico at the very top here to Lake Chapo, a small lake that is located around this area in the Los Lagos region. So these 23 lakes of nearly 15,000 lakes we have in Chile form the largest freshwater district in the country. And these lakes are characterized by being pristine ultra to oligotrophic lakes that provide really invaluable ecosystem services for our country. So we have a huge water reserve in this area. However, due to increasing pressures by the conversion of natural forests to plantations and agricultural lands, also increasing urbanization and industrial activities, these lakes are becoming threatened. So this image also provides a view of some of the changes that have been occurring in the last 40 to 50 years. So if we look towards the valley, this is where intervention has occurred. But if we look towards the mountains, the Andes Mountains, we can see how this landscape was before the changes. So as you can see, the changes around the lake are quite different from what it was once in a day, once a day. So one of the examples we can give on how these changes have had an effect on our lakes can actually be described by introducing you to Lake Villarrica. This lake has shown signs of rapid eutrophication with cyanobacterial blooms formations by Dolichospermum that has become very frequent and more persistent over the years. So this particular lake is transitioning from an oligotrophic state to a mesotrophic state and has become quite it's quite severe, the blooms that are occurring in this lake. So this year the bloom we had a huge bloom in Lake Villarrica. It actually started around Christmas time last year, and it persisted until about February, where concentrations of cyanotoxins reach levels above recommended thresholds of the World Health Organization. This monitoring was done by our environmental the government, the Seremi de Medio Ambiente it's called, and which are always monitoring these environmental changes. So although we also have the General Water Directorate, these are the entities that are responsible for monitoring our lakes. And we have a monitoring program, a national monitoring program. However, the lakes that we are currently monitoring are only 23. So these are the North Patagonian lakes. And the quality of the data is unfortunately not continuous. So we have a lot of gaps between years. They also monitor only 2 times a year, often during spring and summer, and these monitoring do not match with satellite overpass, for example. So so it's quite difficult to be able to use this information for our studies. We also have failure in equipment, quite difficult weather conditions, and also some financial aspects that make our national monitoring program a little bit deficient. And in addition to this, of course, the program that we have does not always capture the extent of what's actually occurring. And this this monitoring program also leaves the vast majority of our lakes without really regular observation, making it challenging to detect and respond to environmental changes and water quality data issues quite promptly. So we need to expand our observations over our waters. So due to these many limitations, there is of course a need to explore new methods that can provide a broader or frequent overview of the health of our freshwater ecosystems. And although satellite remote sensing is not a replacement for traditional monitoring, the technology offers an enhanced perspective for early detection of problems such as algal blooms or other signs of ecological stress. So the information gathered from remote sensing can be instrumental in aiding water managers and decision makers. In essence, the integration of these technologies to our water monitoring framework would represent a crucial step towards a more proactive and informed water resource management in Chile. So of course, I'm not the only one in Chile that has acknowledged this, but the research into satellite remote sensing in our country is unfortunately not as developed as in other parts of the world. And here I will tell you a little bit about how the situation is in Chile, and to have a better understanding of our reality. I wanted to show you this plot. This is the annual scientific publications. I only selected years from 2010 until today. For a total of 7 articles. The first was published in 2017. Well, we have one from 1990, but because technology is advancing so fast, we kept it from 2010. So these articles are mainly contributions from students from the University of Concepción, and this is where I study, and this is also in collaboration with the Center of Water Resources for Agriculture and Mining, the CRIAM, which is also led by the university. So we kind of see a tendency here that most things might be coming from the university, from students in the university, okay? So we have a positive tendency, and this is really good, and we hope that this will be continuing in the future years. And in terms of the networks that we have formed internationally, we have collaborations with 5 countries. We know that publications from Cuba here are actually developed by international students that are from the University of Concepción. So I'm not sure if I actually can say that this is a contribution from another country, but we also have contributions from Italy, France, and Spain and Venezuela, which is great. So I'm personally hoping to add a little bit of color to this map, so to collaborate with international researchers. So as for the characteristics of the publications, we can mention that most of the research have been achieved by applying empirical algorithms for estimating, for example, turbidity and chlorophyll A. Most studies applied also land-based atmospheric corrections, such as the dark object subtraction method by Chavez. A positive aspect is that 2 of the more recent articles have applied AquaLight, so something in the right direction. The first study that did this was for HAB monitoring over Chilean coastal waters with collaborations from Isabel Caballero from Spain, which might have been a result of this collaboration, which is really positive. Nonetheless, we still lack validation for atmospheric correction and the development of biooptical models, which are of course needed in the field. And through this overview, we can clearly see that the limitations that we are currently facing. And this really turns it into this visual cycle we can see here. So most research team working in the field do not have access for radiometers. We don't have radiometers handy or available here in Chile at this very moment, which we need for validation of atmospheric correction. We are also limited in that we don't have access to equipment for IOPs and therefore not able to use biooptical models. So 2 very important aspects of remote sensing. We also have seen that international collaboration is still lacking from the map I showed before. So this is actually much needed guidance for our research efforts. and but also while understanding our limitations. So improving collaboration would actually benefit us tremendously. First, to point us in the right direction, and also by maybe facilitating training opportunities for the correct use of, for example, radiometers, which is really important. So here we go, and the cycle continues. Let's see. So so most of our knowledge is gained through reading, and there are many studies that provide insights on atmospheric correction. The most recent knowledge that we have has taught us that validation of atmospheric correction is or should be a prerequisite for our workflows. Within the water-based atmospheric correction methods, C2X is one of the most recommended for inland waters. Some limitations in this area are, for example, sanguine correction, which is only provided by Aqualight at this moment. And regarding the land-targeted atmospheric corrections, these are methods that are not usually recommended for for inland water quality studies or for waters in general. So also another thing is that the top of atmosphere images are still being used, and in some cases also preferred because of the complexities involved in retrieving radiometric data. So these are actually quite straightforward. We do have an idea of what to do and what not to do. However, advances in cloud computing and also the computer capacity has enabled the use of machine and deep learning models that are ideal for modeling complex nonlinear problems. And because of this, many studies have recently been published for estimating water quality over inland waters using these new opportunities or new methods. So much of the gain of these techniques is that they can significantly improve the performance of traditional and state-of-the-art models. And for us, more interestingly, much of the research that at least I have come across, have stated that machine learning methods might be robust enough to be less susceptible to atmospheric distortions. So this was quite a positive for us. In fact, many of these studies claim that center-core, which is a correction for surface reflectance, have yielded better results than other atmospheric correction. So this would actually mean that I could use center-core for my lakes, and that atmospheric correction would just not be an issue and I could just forget about it. But I did start to have some questions, and for example, how can these models achieve this if we know that they require large amounts of data? I mean, we know that this is a limitation for inland water studies in general and globally. And how can these models account for variability in reflectance in the water? We have also learned that atmospheric correction has to be calibrated locally. And how does it really deal with the complexity of case 2 waters and the water leaving reflectance, which is needed for these methods? So this is where the second part of my presentation starts. Here we wanted to find a very simple method to actually understand a little bit more about the performance of robust machine learning models developed using different atmospheric correction processors, and also taking into consideration, of course, all the limitations that we have in terms of equipment and available data. So our hypothesis is that despite the potential of model robustness of machine learning techniques, atmospheric correction is likely essential for accurate plume intensity predictions and can be evidenced by regular sensitivity analysis metrics. our objective was then to evaluate the sensitivity of machine learning models to atmospheric correction methods for bloom intensity classification. To be able to develop a data set, we needed a lake that had several images available with bloom conditions. So unfortunately, after scanning images over Chilean lakes, due to cloud cover, surface sun-glint wind, and lack of clear bloom conditions, we actually traveled outside of our country to find a lake that would provide these conditions. But we still selected a lake from another underrepresented country in remote sensing of inland waters and stuck with Lake Amatitlán in Guatemala. We chose a very simple classification approach to select our targets. We used 4 machine learning models, and finally we classified the images to analyze our results. So I will explain the methods more in detail, but first I'm going to give a short description of Lake Amatitlán and why we chose this lake. So Lake Amatitlán is a small lake located about 24 kilometers of the city of Guatemala. This lake was once used for potable water, but due to the pressures the lake is submitted to, it has deteriorated, and it's actually quite to an extreme level. This has translated to very frequent blooms, usually by Microcystis aeruginosa, and measurements of cyanotoxins have been done and have been recorded for about 90 micrograms per liter, which is quite a lot. In addition, although there are many efforts to remediate this lake, this hypertrophic lake, the uncontrolled inputs of wastewater, illegal dump sites along the tributary rivers, and uncontrolled land use, the lake is currently suffering. So this lake was selected due to these conditions, as it provides an important number of cloud-free days with evident blooms that we were able to use for developing our dataset. In addition, we are in contact with the authorities for the sustainable management of the basin of Lake Amatitlán, the AMSA, who monitors the lake and has water quality data that we are possibly have available to us quite soon. So to explain a little bit how we developed our data set, we actually use a rather intuitive method to distinguish between different intensities of blooms using TOA false color images, and we use Sentinel-2 for this purpose. The false color composite is actually something that is quite common to use to represent different severities of blooms. We can find many papers that relate these colors to the presence and absence of blooms, that has been used for example, to identify absence and presence, and also classifications based on trophic state index, etc. So visually, we can actually really see where the blooms are occurring. So this approach was based on distinguishing between classes or colors in this case by selecting these red or fuchsia colored pixels for a class, a darker shade of these colors like we can see here for another class, and then very dark pixels for the third class. So even though this is a really simple approach, we think that it can have several benefits for studying lakes. So for example, this does not really require in situ water quality data. However, it is of course preferred. We could use these classifications to be able to quantify the extent of bloom formations, and this will provide will still provide really interesting data for managers. And this selection method could provide a simple way to actually analyze and access remote lakes. So, and this the final part here is really interesting to us because of the difficulties we have to access some of our lakes. So here you can see the data sets that we selected. There are seven images. 5 of them were randomly selected for training, and 2 we left for testing. So we wanted to assure that we were working with truly unseen data when developing and analyzing our models. We downloaded the reflectance from the bands 2 and 8 to 8 to be used as our main features. And for atmospheric correction, we focused mainly on the C2RCC family. So C2RCC, C2X, and C2X complex, extreme complex. And we also added DOS and CentuCore because DOS is a method that is very much used here in Chile for waters, and CentuCore is recommended by machine learning methods. So we wanted to have these or include these to compare it against the TOA dataset. So the process was quickly, the atmospheric correction process quickly showed us that we had problems with our data set from the beginning, and actually showing that we had non-valued pixels for class 0. This information was actually really beneficial to us, as this clearly showed that class 0 corresponded to a surface bloom, which C2R, CC, and C2X were really quickly to flag. For this reason, we eliminated this class and kept working on a binary classification instead, so an even less complex model. So we use this data set to add additional complementary features targeting well-established chlorophyll A and water algorithms, such as the normalized difference chlorophyll index, the two-band algorithm, the slope algorithm to map algal blooms, and the normalized difference water index. We pre-processed the data to scale it, used smooth to account for class imbalance, and applied a principal component analysis. We did this to select the number of principal components by using a minimum of 70% threshold of cumulative explained variance, which is used in many studies. We don't have kind of a threshold for remote sensing of inland waters or for water quality right now, so we kept with the 70%. And later we used the number of principal components to reduce feature dimensionality for model development. For for machine learning models, we selected random forest, gradient boosting, and XGBoost for their reputation of being very robust to outliers and also for overfitting, and selected the support vector machine or classifier in this case for a little bit more of a simpler method. We then developed the best possible models, and we used hyperparameter tuning to do this. So a lot of computer sources were used to develop this study. And we also submitted the models to a 5-fold cross-validation to finally analyze our results through sensitivity analysis through the complete unseen independent test set for these commonly used sensitivity analysis metrics. The final step of this work was to deploy the models by classifying the images to see how well the models actually worked. So let's check the results. So this table shows the different cumulative explained variances we achieved with the different data sets by using one principal component. The 70% threshold that we set as a criteria did not hold for the water-based processors, AquaLite, C2RCC, C2X, and C2XC. So this, we believe, implies that the water-based atmospheric correction methods are just more complex than the TOA and the land-based processors, which is why we might be getting these results. So when we applied two principal components, all processors were able to achieve that threshold we had set. And even the models were kind of similar. There were similarities between the results when applying the two principal components. So this was what was used for model development. This let's see. So this graph here shows the global results. This shows the overall accuracies of the models after sensitivity analysis. I'm only showing overall accuracy here, but all the other metrics that we use also had similar. We had very similar results across models. So most of the parameters were also in for example, the 90s for TOA dataset and so on. So looking globally at these results, we are able to recognize that the support vector classifier is the overall best result across the TOA and the other processors. This model seems to be less susceptible to atmospheric distortions. So this is quite positive to know. But based on the global results, we do see that the land-based processors do have the best results. These models, in addition to Aqualite, also have kind of similar spatial results as well through the classifications. Here I have only kept the best model that we had, but these are the water-based processors. If we look a little bit closer to the water-based processors, Aqualite offers the best performance within this group, followed by C2X, C2XC, and C2RCC. The latter, this is quite consistent with what we know about these processors. So the neural nets of the C2RCC processors are trained over moderate to extreme values to perform atmospheric correction. So in particular, the C2X nets is recommended for waters that have high concentrations of suspended material and chlorophyll concentrations, while C2X are recommended for complex inland waters. So both of C2X and C2XC or complex kind of fits well into the description of the Lake Amatitlán. If we just base our results on this analysis, we would probably define those as the superior model. However, we believe that something very interesting is happening here that I will discuss in the next slide. So in this study, the top of atmosphere TOA reflectance is, the TOA atmosphere top of atmosphere reflectance is raw satellite data, so no atmospheric correction. In our study, it serves as a baseline or a worst case scenario where the impact of the atmosphere on the satellite imagery is not accounted for. So the fact that the DOS, Centicore, and Aqualite methods produce results very close to TOA could imply that they might not be sufficiently correcting the atmospheric effects for the specific case of inland water studies, or in this case, Lake Amatitlán. So these algorithms, while generally effective in other environments, may not be as effective for Lake Amatitlán. So to actually explain this further, we can use the survivorship bias, where analysts actually initially recommended reinforcing parts of a plane during World War II, I believe it was, reinforcing the parts that of the returning planes that show the most damage. However, it was later understood that the undamaged areas were actually more critical, as planes hit in those areas did not return. So if we apply this analogy to our results, the atmospheric correction methods that appear to be effective in this case, which is dose centricore and aqualite, which closely resemble the uncorrected TOA results, might not actually be addressing the key atmospheric issue. The true effective correction would then lie in areas or processors that would otherwise be overlooked in the analysis. So we still have to look towards the water-based processors. And so to conclude, this exploratory study showed that thus Centicore and Acolyte are not adequate to address the unique challenges presented by Lake Amatitlán, and this is because of the convergence with the TOA dataset, which has no atmospheric correction. However, the land-based processors can be used for mapping superficial blooms, and this is due to the particular characteristics that they are actually on the surface of the water. So it's still we can still use them, but we have to know where to use them in this context. Also, sensitivity metrics may not always provide the accurate result for evaluating classification of bloom intensities across models, especially developed with the data acquired from different atmospheric correction processors. So this is particularly true when we are only determining the results based on the highest resulting metrics. And sorry. And also, maybe when radiometric data for validation of atmospheric correction is not available, which happens in many countries, we might be able to analyze the results or the results based on the survivorship bias analogy. Maybe this is an appropriate way to analyze it when we don't have any other alternative. But this should, of course, only be considered when applying machine learning methods due to the amount of data that we can acquire. But we believe that the deficient result for the water-based processors imply the need for a more robust method to classify bloom intensities or severities. And we believe that this can be done maybe by using the same method, but applying, for example, semi-supervised classification or to really separate the classes. For our future perspectives, like I just mentioned briefly, I really want to start exploring semi-supervised classification for developing dataset for water-based processors exclusively. I think I just need to move away from the land-based processor at this moment. And also the classification, do classifications based on defined thresholds of, for example, the normalized difference chlorophyll index. Maybe these ranges could be really interesting to explore to be able to separate the different signals that we're getting. And also, we want to provide a better understanding of feature importance for these models to reduce dimensionality, as well as how much data is actually needed for these models. And this is also when including seasonal variation, which will be something that will be a little bit of a challenge. So finally, and very important part of this would be, of course, to find collaboration to validate these methods with radiometric data. Well, these are some of the references I've used in this presentation, and I just wanted to thank again and give thanks again to the HEO AquaWatch community and the organizers for providing this very important platform to inform and discuss our research and what we are doing here in our country. I also like to acknowledge, of course, all the projects that I'm working on and that are supporting this research. Also, I want to give a huge thanks to everyone that has been truly supportive throughout my studies and work, my colleagues, but also my friends. Finally, Rabia and Yulun, my mentors for this talk, thank you so much for your support during this last month and for giving me great suggestions on improving this talk and comments about my work, and also for your patience. It was hard, but I thank you a lot. And I really appreciate the time and disposition for helping me. And I'm sure we'll keep in contact and hopefully collaborate sometime in the future. So thank you so much for this talk, and thank you for listening. I believe that we now have a few minutes for Q&A.
Yeah, thank you so much, Daniela, for your presentation. I see that Steve already raised his hand. So Steve, you can unmute yourself and ask your question.
Thank you, Igor. Great presentation. I appreciated it.
Thank
I
you.
just had a couple of quick questions. Are there like algal mats or scum that form on this lake? I mean,
Yes.
can you differentiate between the mats and say just the algal concentrations in the water column? And then the second
Mhm.
question is you touched on seasonality. Is there much seasonality a lake like this? I think it's about 15 degrees north latitude, but it's
Yeah.
also high.
Yes.
So
This is actually why we selected the lake as well. Um, as for to classify, we know that there are superficial blooms here. So we know that they have floating algae. The transparency of this lake is a little bit less than a meter. So we do have quite severe conditions. Um, so I did not show all the images that were classified, but we were actually able to see that the C2 extreme complex algorithm was actually quite good at distinguishing between and kind of framing the superficial bloom. So we have to actually take a closer look on that, because that was something that we didn't expect to happen. The other algorithms, like I said, we do have superficial blooms in this area and also beneath the surface. So we have several conditions that we can explore in the lake. And as for the seasonality, yes, we did use Lake Amatitlán because of also the variability, but they do have two marked seasons. So they do have some cold seasons, for example. So I have a friend that has explained very well how the weather is over there and how this lake is too. So we still believe that we have to do introduce more months, for example, or to check how we can separate the different spectral images that we are getting from the different processors.
okay, thank you.
Thank you.
Anyone else? Rabia?
Hi, Daniela. Excellent presentation. I believe like we still have time left, so I would want to know more about, because you're working in Global South. So tell us a
Mhm.
little more about like the challenges you're facing there and how are you like finding a way around. And also, what sort of more resources or instruments, if you had, will make your research like more accurate or more easy for you to carry on?
Yes, so I'm really lucky because I'm working within many projects that are funded. So right now we do have funds available to do monitoring campaigns. We have equipment, we have a boat now, and things like that, which are very positive things and things that we didn't have before. The main problem here in Chile is that the location of the North Patagonian lakes is a place where we have a lot of cloud cover. So we have to, many of our monitoring efforts, we have been on site monitoring, but we have, for example, really strong winds um, um, or very, and also very strong sun glint that so we can't really use the data that we have collected. I mean, we know that this data is not going to be the best. So, and the way to work around this is that I've actually moved a little bit northern and other Araucanian lakes here and around the Muco. We can find the Lake Lanalhue. This is a lake that also has oligotrophic conditions, but during the summer and also during to urbanization, it is also starting to have blooms by Dolichospermum. Here we have an area of indigenous people, the Mapuche, and they really and this has created a little bit of an they protect the lake, so they don't allow to enter with boats and things like that. So that has been a challenge for us, and also of course the lack of radiometric data and equipments. We know that we can have we I know somebody that has that equipment, but it's one person that I know. And the thing is that these are so expensive, and Chile does not expend much money on research. So lending out these really expensive equipments is really something that most don't do. So they keep it within the group that they work with. So it's really hard in that way. But yeah, so funding for equipment and I would like to try to find, for example, also study the spectral signatures of our waters. We do have, for example, I've monitored lakes and I also retrieve samples of the blooms, so I know what kind of blooms we have. So maybe we can try to do some matching there and see what we can find from there. But yes, very exploratory and very maybe creative ways to try to deal with our problems or our field.
Danielle, there are two questions in the chat. I think the first one you already answered is from Mary Beth, asking if there is a possibility to borrow a radiometer for your fieldwork or
Yeah,
loan.
yes, I'm working on it, but I think it's very difficult. But I'm working on it, and I have the contact. So we are hoping that I would be able to loan it during for this year. I'm still I don't have any answer for that right now. But I'm hoping that everything will go work out. And
The second question is from Annabella. Annabella, do you want
Mhm. Oh,
to answer to ask it yourself?
Yes, well, congratulations, Daniela. Very nice your presentation. Very important this kind of studies and very clear. So I like it very much. I have a question, but maybe I understood bad something. But the question is, when you analyze TOA performance
mhm.
without atmospheric corrections, you use two components of PCA, and I didn't understand well that because
Mhm.
maybe when you do the principal component, the composition, you are taking out the atmospheric effects. That's a
Mhm.
question. I don't know if you understand it.
Yes, so actually the results from one principal component and two principal components for the TOA datasets, and also also the land-based processors, they didn't really improve that much. Um, I don't think that this was possible, and also this I think it's because of the complexity of Lake Amatitlán as well. I think well, if we see, for example, the classifications that we had of the lakes when we used the land-based processors and the TOA image, um, the the algorithm was mapping mainly water, and did not see any different things within the water. We had really different results for the water quality processors, which I believe is because they are capturing more of what's going on, really, that more than what we can see with, or what we can differentiate with our eyes. So basically I think that it might help, but I would only recommend this or using those products for surface blooms, um, not for within water. Thank you,
Yeah.
Annabella, for your question.
Thank you to you. And we are the country next to you,
Yes.
Argentina. We have a radiometer. Maybe we can talk. Maybe there can be any chance to lend you. I don't know, but we can talk
Yes, that
later.
would be amazing. That would be really good. Nice. Thank you.
Well,
Oh, we have. There's another question in the chat. Dr. Lee, do you want to ask it yourself or should I read it?
Oh,
So Daniel, there's another question in the chat. Do you
okay.
have information on how historical cyanobacteria blooms in this lake is comparable with current cyanobacteria status?
Mhm. We have some environmental documents that have analyzed the lakes, but unfortunately they don't analyze what's in the lake. They do have concentrations of chlorophyll, for example, turbidity, transparency, and nutrients. But the information of what is causing the bloom has not been recorded, and that is actually something that is being done just only recently. And because of the kind of the new knowledge that we have about the health issues that cyanobacterial blooms or toxic cyanobacterial blooms have. So at least each time I go to monitor, I do take a sample to see what we have, and to be able to have that kind of build a, database. So we have at least that kind of information, which can be useful as well to study this spectral signals over the water. And that's the information that we have at the moment.
So thank you so much, Daniela. We reached 1 hour of this presentation, and I think Maribeth, this is what we have, right?
That's correct. Yes, we can close.
So thank you so much for
Great.
everyone who joined, and thank you so much, Daniela, for presenting and sharing Water Talks. And in February we will have our next Water Talk. So keep the this data in mind that we will have a third talk on the WaterTalk series.
Thank you very much for listening.